Okay, let's get going. Everyone hear me okay? Yeah, it's a nice small room. So they're giving me the after lunch slot and the small room. Okay, so I'm going to be looking out for people falling asleep. So today we're going to have a little chat about building fault-tolerant microservices. So it doesn't matter too much if you're not interested in microservices. Virtually everything I'm going to talk about is applicable for building monoliths. It's just that most of it happens a lot more often when you separate your software into lots of small services. So it's just going to happen more, and it's going to be more important to you. Before I go on about it, I'll tell you a bit about who I am. So I work for a company called DataStax. Anyone heard of DataStax? More hands every time. So they're big in the US, and they're getting bigger in Europe. So DataStax are the company behind, or the company that contribute most to Apache Cassandra. And they build products on top of it, which you can buy and get support for, etc. Okay? I work as an evangelist there, which means I come and do things like this. I also build the test double for Cassandra. Has anyone heard of a test double, that phrase? Oh, you will have by the end of this talk. Most of this talk is actually about the system which I built at Sky. Now, Sky, obviously most people aren't from the UK here, are the main television provider there. So, and they, like Netflix, provide an online version. So you can watch it on your iPad, your Android, your web, or even a lot of set-top boxes now stream over the internet rather than, say, through a cable or via the internet. Sorry, via the satellite dishes. And we're essentially building that system. And we're replacing an old system, what we probably call a monolithic system, with a set of small services, which at the time we didn't call microservices, but I've later found out that they were microservices. And that used a lot of Cassandra, hence why I now work for DataStax. So the agenda. What are we going to talk about? So first, I'm going to kind of set the scene. I'm going to describe the system that I was replacing, and I'm going to decide the system I was replacing it with, and all of the benefits. But most of the time, I'm actually going to talk about all of the downsides of separating your system into lots of small processes, aka microservices, and what developers need to learn, and how we need to program differently and handle failures differently. And I'm a big tester, so I love having automated acceptance tests for everything I write. Okay? As far as I'm concerned, like features in software that don't have an automated test are just rumors. They're not actually software features. And I've come to the conclusion that faults should be tested in just the same way. So no longer will I allow someone to say, oh, it was a network glitch, it happens once a month. If there was a network glitch, then I want to be able to recreate that deterministically and test that my application handles it correctly. And a lot of the talk is going to be about how to recreate things which people say only happen in production. So what did we start with? So Sky initially thought maybe internet television's not going to be a big thing. Okay, 10 years or so. Outsourced it, and a piece of software which was built, which was based on, deployed to Tomcat, typical kind of JE architecture, had lots of session state, and it relied on Oracle. And lo and behold, internet television got popular. Okay, who knew? Okay, you tell someone 20 years ago that they'd be watching, Game of Thrones popular in France. Yeah, Game of Thrones on an iPad. They'd probably say, "What's Game of Thrones and what's an iPad?" But you get the meaning. So the same to scale this as more users started using it. Something like this happened. The little Tomcats multiplied. We deployed lots of them. At the time I left Sky, there was about 60 of them, and that was fine. It did scale reasonably well, okay? But what didn't scale was our database. So invariably, it would fall over in a heap because the database would fall over, okay? It wasn't designed to have 60 processes all hammering it with, many concurrent reads and writes. And if the database didn't fall over, what usually happened was one of the Tomcats fell over. Or perhaps we were just doing a release, because people think, oh, fault-tolerant software, I'm trying to handle hardware failure. But as far as I'm concerned, if you want to build always-on software, you're as much worried about, releasing your software or doing an operating system patch or something like that. At some point, you need to turn these off. And what normally happened when a couple of our Tomcats fell over is obviously the load would get rerouted to the other ones. Now, we had sticky sessions and state because it wasn't originally built to be a horizontally scalable service. So when a couple of them went down or we had to reboot them, then suddenly say a 60th of our traffic would suddenly get routed to the others, and then all the customers would have to log in again. So what normally happened was this. All the Tomcats fell over, and then we had downtime. So we had some ideas, okay? We wanted to replace this with a system which was horizontally scalable. And you can't really argue with that, can you? It's just quite difficult to achieve in practice, okay? So we wanted to be able to scale each part of the system independently. So we weren't going to build a horizontally scalable monolith. Our idea was to build a horizontally scalable set of services. And we only scale the ones that need scaling, okay? And the other thing we needed to do was replace the database. Because it's very hard to run a traditional database, just like our software was designed in a time when we were going to put it on a single computer and have 100 transactions a second. It wasn't designed to run across many computers across multiple data centers. Okay? So we were evaluating different databases. And we wanted a durable database which could run active-active across multi-data centers. And there aren't really many that do that, so that's why we ended up using Cassandra. But we didn't want to move all in one big bang where we suddenly turn customers over to the new system. So we started doing things which I think has been coined as the term strangulation. Now, we didn't go and strangle our customers to stop them using our service. We just pulled bits out of the monolith, mainly the bits that hammered the database, because that was kind of our scaling impediment. So there was a bit which had many, many durable writes. It was about what customers are up to. And we needed to be able to save that durably across multiple disks because we'd end up billing on it and things like that. So it had to be right. So we pulled that out and made the monolith call out to it. Okay? We'll call it this one. The next thing we did was move out something which required a lot of processing. So at times our Tomcat servers would eventually fall over because they'd be CPU bound. So we moved some more out. And that essentially bought us some time. Because we didn't want to keep doing this because strangulating a monolith is very possible, but it requires a lot of testing. It requires a lot of effort, and you're typically doing it against a system which wasn't designed to be that testable. So this kind of architecture got us so far, and it gave us time to replace the entire thing. The whole idea was to keep reusing these bits, but replace these bits with something new. And this was quite possible for us to do in a non-big bang way, because what happened was the back-end services which allowed people to watch television online were used by iPhone apps, multiple of them, one for sports users, one for movies users. They were used by web pages, tablets, lots of different front ends for the same back-end. We even had a Windows mobile one which about 8 people used. So even if we replace the back-end, we can actually move people over slowly to the new back-end, as long as we keep the API roughly the same. So what we started doing is building this architecture which involved lots of small services, independently scaled, so we might have 50 of the audit service, we might have 10 of the user service, and typically all of them had their own Cassandra cluster. Because just like we wanted to be able to deploy and scale the services separately, we wanted to be able to have database choices separately, or to release and upgrade the database, or change schemas. So we didn't use, say, the same cluster, we used the same Oracle for everything. Okay, so we kept them separate. And we ended up running different versions of Cassandra for each service. So we didn't have to upgrade one when we wanted to use a new feature from a new version. And it got bigger, so we started adding them. Some of them were stateless, so some of them didn't have a database. And basically there was quite a few orchestration ones which just called out to other services, and quite a lot of ones which held reference data. But you get your meaning. And what I'm going to do now is actually simplify that down and use it as a use case for talking about all the things that went horrifically wrong when moving to a microservice architecture. So it wasn't all roses, didn't all just work. There are many things that developers and ops people need to change in their mindset if you're going to distribute everything, okay? So this is the example. It's a very simplified version. So the backends we're talking about don't actually stream television. Okay, that's done by CDNs and all sorts. It's mainly APIs that are managing things like customers. What are you allowed to watch? What devices are you allowed to watch on it? What content should we give you based on the device you're watching? The complexity in streaming television, oddly enough, is not streaming television. It's making sure that people are doing it correctly and they're allowed to and they've paid and all these types of things. Okay, and that's what our orchestration movie player did. A device would call in and say, this user wants to play this piece of content. And it would give all the information back, so the location of the content, the decryption keys, and all that type of thing. And to do that, it would have to call out to a few of its friends. We're going to separate this out. They're going to be separate components. So we had one service which managed users. Okay, Their entitlements, what have they bought? Another service to manage devices. Unlike Netflix, where you can give your password to your friends, you shouldn't. With Sky, you had to have a set number of devices you were allowed to use it on to try and prevent that. And you're only allowed so many device changes per month to make sure you didn't just change it every time you gave your password to your friend. And pin service. So a lot of the content was 18 movies. Surprisingly enough, you shouldn't let 5-year-olds watch Game of Thrones. Okay, so that's what that service did. And that example, while I was still working at Sky, I pulled out and I just created a really dummy version of it so I could show people and talk about it. And all the examples are on GitHub, so you can actually start that very mini small version up. It's not exciting. But these are some of the technologies we're going to talk about today. So I'll do a little, hand votes and see just who's heard of them to know how much detail to go into. So who here uses Dropwizard? Good. And Spring Boot. So Spring Boot copied Dropwizard. Wiremock. So Wiremock is what I classify as a testable for HTTP. We're going to have a look at that in quite some detail. Hystrix. Anyone use any of the Netflix open source? So I'll talk about that a bit today because what I'm going to do is I'm going to talk about a problem. I'm going to talk about how to recreate it. And then I'm going to talk about how we solve it. And most of the time, solving it is using something that Netflix have done. Okay, which is ironic given we're building a online television platform. Graphite is a server for Graphite. So basically, as soon as you distribute stuff, you need to keep a track in a central location of what's going on. Graphite is a server for looking after metrics. And Saboteur, Saboteur. So the first time I gave this, Saboteur was developed by the same person as Wiremock. It's a way to play with networks, so you can recreate weird scenarios. And it was made by the same person as Wiremock, and the first time I spoke about this, he was in the audience, and I didn't know him, so he eventually stood up and said, "Stop talking about me." So this is my little mantra in life, that if you really believe you've got some fault-tolerant software, so who's heard of the Chaos Monkey? The Chaos Monkey was developed by Netflix. It goes around their infrastructure and turns stuff off to make sure that when stuff fails for real, you can handle it. And everyone builds software. So you don't get away with building non-fault tolerant software. We're not going to talk about that type of testing today. We're going to bring it all the way back to, say, your continuous integration pipeline, the building of your code and acceptance testing. The idea of what I'm trying to get at today is, how can you make sure that when you do that type of testing with Chaos Monkey, which goes and turns things off and drops network and all those type of things, how can you be confident that your software is already going to work? Okay? So I'm first going to define a test double, because I'm going to use that phrase a lot. And you've probably heard of a test double, you probably just haven't heard of the name. So if you're going to test faults, okay, and faults of your dependencies, so we're talking about, say, a HTTP dependency, a database dependency, perhaps a queuing dependency. Okay? The first thing you need to be able to do is make them fail in every possible way that they could in production. Okay? And if you use a real version of all of these dependencies, it's kind of hard. Okay? Or if you try and do it in your pre-prod, say, load testing environment, it's really hard, and things might only happen, say, once a week or once a month. The idea of a test double is to, as far as your application is concerned, be the real thing. So it's not mocking out like at the class level, say with Makito. It's the real thing, and you can actually prime it to do all of the crazy things. Wiremock's the one I'm going to go on about for HTTP. Stubbed Cassandra was the one I built when I started working with Cassandra. I know it's what I used to spend my evenings and weekends doing. Now I get to do it during work time. And I've just started playing around with one for Kafka, but I haven't got very far with that yet. And the test of I don't know if this was where the phrase came from, but I got it from this book. Has anyone read this book? It's quite old, but you should go and read it. It's really good. It's talking about this, but say 10 years ago. It's talking about a monolith talking to a monolith. It was an airline booking system. And maybe what they were talking about, same kind of thing. Maybe it happened once, but maybe it happens once a month. All I'm going to say is all the stuff in this book about how you should test your software, it's just going to happen a lot more when we start breaking it into lots of services. And each of your user transactions ends up actually being 15 network calls. Okay? So these are the types of tests that we're going to try and build. So I classify them as technical acceptance tests. So I'm assuming that for all of your actual business functionality, that you've got tests for it, right? I don't really care which framework, or whether you use Bash or Perl or Cucumber or JBehave. Don't really care as long as you test it. What I'm going to talk about is building the same type of tests, but for what I would classify technical acceptance criteria. The kind of things that, engineers, architects, whatever, will come up with and say, how should the system handle under faults? Okay? And what do we start with? So you've got movie service. And this movie service is going to be tested, and the built version that you deploy to production, I want to test that. Okay? I don't want to test that, say, the mocking out drivers with things like Mockito. I want this to be the same jar, war, whichever kind of executable you're using that you use in production. Okay? For each of the dependencies, I'm going to use one of these test doubles. And the movie service didn't talk to a database, so this is just going to be using Wiremock to mock out the pin service, the user service, and the device service. And all the acceptance test really does is prime the dependencies to do whatever you want, hit the service, make sure it does the right thing. Simple. Okay? I always try to extra point out here that I do mean that this is real at the protocol level. As far as I'm concerned, when you bring, say, a driver or a library into your process, so Apache HTTP client, the Cassandra Java driver, that's part of your process, and I think you should be testing it, okay? Mocking that out is dangerous, okay? Because any bugs in there, or just misunderstandings of how it handles failures, will lead to your users not getting service. So it's a bug in your system as far as I'm concerned. So I always want real protocol stuff in here, okay? And I'll probably run these type of tests after my Unity integration test. So because people like but nice lists in presentations, I've come up with 6 areas which I think are very different when you start doing microservices or distributed computing. I won't read them now because we're going to go through them. So the first is timeouts, SLAs. Who here, when they build a piece of software, is given or makes up because they weren't given, say, an SLA for how quickly you should respond, say, 200 milliseconds, 5 seconds? Anyone? Okay, so timeouts are probably the worst implemented feature I've ever come across. Okay? And up to about 18 months ago, every piece of software I built that I claimed to have a timeout would not have timed out under all circumstances. So there's lots of Christopher Beatty buggy software out there that will have a network glitch and not time out correctly. Okay? And when we're talking about, say, the user service calling out to the pin service, these are the types of timeouts I'm talking about. So how do we do this? So because it's over TCP, we normally start with network level timeouts. So the first 2 that virtually every single, say, database driver or HTTP client is going to have is a connection timeout, the amount of time to establish the TCP connection, and a socket retimeout, the amount of time which is going to wait for some data to come on your socket. Simple, right? You set these, and the maximum that this request would take, plus any garbage collection, etc., and any processing, is going to be what you set them to. If you do rely on network level timeouts, then eventually your customer is going to be pretty sad. I always put up the sad panda when you have something which you don't expect. But you shouldn't really worry about the customer, you need to worry about yourself, because eventually you're going to get shouted at, because you've claimed, oh yeah, it's definitely going to time out. And especially when you think about it, when you're deploying multiple versions of the same application, which you often are when you're doing this microservice architecture, then you really want to time out, because chances are there are 15 other versions of the application that the request could get routed to. So being slow is as bad, if not worse, as failing. Okay, so why is it not timed out? Why have you not met your SLA? And I'm happy to fail within that time. I just don't want to take any longer. So the next thing that you generally get to is resource acquisition. So any HTTP client you use, any database driver, oddly enough, if you fire in 1,000 threads, it's not going to make 1,000 connections to your database. If it does, then you should stop using that driver. And so what eventually happens is they're all used. So let's say that our Cassandra database driver or HTTP client will only make 10 connections, and the 11th one comes in. Something's going to happen. It's either going to get rejected, or it's going to block, or it's going to get put inside a queue. And when you think about it, your thread here has never ever gone to the network layer yet. So you definitely haven't started these network level timeouts. So you can spend a lot of time just waiting for a connection. And you need to look at the drivers you're using to see what they do under that circumstance. So even if you fix that and you set that, you can be the hero. You fix the timeout issue that happened once a week. Okay? But then a month later, the sad panda comes back because your service hangs again. You think, oh, it's definitely going to work now. Suddenly, because you were the hero last time, you're designated the expert, brought in on the weekend to come and work out what's going on. So what could have gone on? So I like diagrams. So actually, this happened, and they didn't bring me at a weekend. Fortunately, it was a Monday. So I started drawing pictures, okay? I was thinking, so how does it work? What is the actual time spent, on a network call? And I think, assuming I'm using some driver, then, yep, I've got the resource, okay? So I'm dealing with the fact that this driver is only going to connect to the database 10 times or create 10 HTTP connections. Set that timeout. Connection. So perhaps the connection wasn't established yet. Perhaps it was stale. I'm going to set the socket time. I'm going to set the connection timeout. And then I send the request, 500 milliseconds. And this can't take more than 700 milliseconds, right? It can't? Well, most of the time it will take less than 700 milliseconds. But a lot of the time it won't. And it might be, say, 1 out of 1,000. So who here records and graphs percentiles? Anyone? So you look at your 99th percentile. But when you've got to think about what they really are, because that's 1 out of 100 or 1 out of 1,000 if you go 4 nines. So if you're building a web service which has, I don't know, this one in particular that was at peak 40,000 TPS. So suddenly your 99 and your 99.99 percentile for this happening, for this taking longer than 700 milliseconds, was happening 50 times a second. Okay? So it's not that network glitch anymore. And this all happens because suddenly we've turned one user request into 18 network requests. That's one of the kind of trade-offs that we have from moving to a distributed architecture. What can really happen is this. Okay? So you send your request out over the socket, and think about what a socket read timeout is. It's the amount of time that your network layer is going to wait for some data to come. Okay? It knows nothing about the application layer. It doesn't know anything about what massive JSON response. We all love JSON, don't we? And what can actually happen under, say, a saturated network, or say your dependency is overloaded, is small amounts of your response come back at a time. Okay? So there's never a period here where the network layer has not received something within the socket read timeout. Okay? The first part of the response, not the full response, came back in 400 milliseconds, then 300, then 450, and 499. And this request with a big enough payload will never actually end. But this was a theory, okay? I just thought maybe this is happening. So how would we prove this? We'd probably we'd go to our ops guy and we'd ask him really nicely to leave on TCP dump forever until it happens again, okay? And he's probably going to tell you to go away nicely. So what we want to be able to do is recreate these types of scenarios in a test environment deterministically and write a nice acceptance test for it, okay? So we can prove that this could have caused the 30-minute or however long delay it was, and make sure that all of our callouts, all of our interactions between those services will never fall foul of it. So how do we do that? So a set of tools. Who uses Vagrant? Vagrant's a really cool tool. I know there's Docker, etc. come along. Vagrant's a really nice tool. And it enables us to spin up VMs in our, anytime, but I like to spin them up during continuous integration pipelines, okay? Because I want to be able to recreate something from scratch, known time, and then do stuff. The other reason that we're always going to use Vagrant for tests like this is no one's going to let you do what I'm about to say, okay? The ops people is not going to let you run commands like TC and IP tables on your continuous integration server. If they do, you should get a new ops person, okay? Because you don't want to be running these. You could easily cut off traffic to the box and someone would have to go and find it in Amazon, okay? So we don't want to do this. Saboteur, which is basically just a wrapper around a few Linux commands, okay? IP tables you'll find on virtually every Unix and Linux system. It allows us to cut off traffic, okay? And that's not going to recreate this scenario, though, is it? Because if we cut off all traffic, then the socket read timeout will work, because it's not going to receive anything. TC, which is a Linux traffic shaping command, which is fun to play with a very interesting syntax. That enables us to do more interesting things. It allows us to, say, at a certain probability, delay traffic, or delay each packet. So you can see what we can actually do here. We can actually deterministically with TC cause that thing from the last diagram, okay? We can actually make this happen with TC. What Saboteur does is give you a nice API. So it's a little Python program. It has a HTTP interface which has, nice operations like delay traffic, not a massive long page of, command which you pass to TC. We're going to use Wiremock to pretend to actually be the service. And then in the examples on GitHub, it uses Cucumber. But don't worry about that. I really don't care which acceptance test framework you use, if any. Use JUnit or Shell. And it starts to look like this. So on the right, however, you don't need to change the way you're normally doing your testing, okay? But what you are going to do is spin up this. This is a VM, okay, with Vagrant. This is slow the first time, but it will spin up in under a second, once you've launched it once. We're going to install Wiremock on it and Saboteur. Okay? In our acceptance test, what we'll do is we'll prime Saboteur to delay each packet by 400 milliseconds or 499 milliseconds. Okay? Then we're going to hit our movie service. It's going to call out. All the packets from the response are going to get changed. So we actually need a reasonably large payload for this. And then we're going to verify that we time out. So we set this to 500 milliseconds, and we're delaying each packet by 499. It's a timeout in just over 500 milliseconds. But if you rely purely on network-level timeouts, this won't work. And it's quite eye-opening, because people generally don't believe you when you talk about this kind of stuff. But then you just show them. You can then whack on TCP dump, put it into Wireshark, and just show them exactly what's happened. Okay? So how do we fix it? So all of the applications that we were building at Sky were all either Dropwizard applications with a embedded Jetty. Anyone use Jetty? No? Tomcat? Okay, any embedded HTTP server that's kind of like servlet-based. Okay, so we were still in the age, and most of us still are, of working with, say, a Spring controller or Jersey controller, taking in a request, being given a thread. Most servers are still, per request has a thread. I realize that there are servers that don't, and we can talk about those later. But for this company, all of them were based like that. So we were Jetty and Tomcat, and it came in, and you have this thread, and it's precious. Okay, that's the thread that you respond on. When you finish we're not really using servlets, we're using abstractions on top, like Spring RestControllers. But as soon as you give that thread away to someone, as soon as you let someone hijack that thread, you can't guarantee any form of timeout, okay? Things will go wrong. So how do we do it? We need to do dangerous things, like calling out to databases and HTTP services, not on this precious thread, okay? That's it. That's all you've got to do. And then you make sure that the request thread times out correctly. There are many ways to do this, okay? You can roll your own, okay? Screw it. I'm just going to create my own executors, my own thread pools. I'm going to do it myself. If you're using modern versions of Spring, you can just annotate things with Async. How easy could that be? But there's a more interesting framework which we use at Sky for all of our interactions between our microservices called Hystrix. And Hystrix is a library open sourced by Netflix, and essentially it's for just this. It is for protecting your application from your dependencies, which I normally say means I'm protecting my precious container thread from daring to go into anyone else's code. Okay? Simply put, all it does is you have a separate thread pool per dependency. And it makes sure that your request thread is not used to make the call out. And then you can time out. And it's got some awesome configuration, like, only allow, you can set the timeout, and you can set it to just turn off that dependency. We're going to look at that in a bit. And we're going to look at an example, and it's not going to be the movie service. It's actually from Spring Cloud Netflix. Okay, so bit of a disclaimer here, we didn't use Spring Cloud Netflix for building the system. This came about after we were almost finished. But basically this is good old Springified annotation to basically remove your need to write any code for this. Okay? And I'm going to show an example of raw Hystrix later on in the slides, but let's look at a Hystrix one. So who's seen a class like this before? A Spring RestController. If you're using Jersey or JAX-RS, it's very similar. You have a request mapping, okay? And your precious thread comes into here, and then we log out to see which thread we're on, okay? Then we call a scary dependency. So that scary dependency, for me, is anything which isn't your code. Any libraries, any HTTP clients, that type of thing. And I find that the best way to convince people to not give this thread away is to tell them to assume that every piece of code that you go into that's not yours is doing this, okay? It's just deciding, if the time's even, I'll return them a nice scary string. If it's odd, I'm going to sleep for a bit. I'm still going to respond, but I'm going to delay that response by 5 seconds. Okay, just assume that's happening. And if we look at the logs from that, you can see we're on, this was Spring Boot, so by default it was an embedded Tomcat. This is what Tomcat calls its threads, okay? And yeah, we can see we're on the Tomcat thread. With Spring Cloud Netflix, obviously you have to put things on your class path and put a magic annotation somewhere. That's how Spring works. We just stick Hystrix command on. This is basically telling Spring Cloud Netflix and Hystrix that this is a scary dependency, and we do not want to let it slow down and destroy our application threads. Okay, and it's amazing what difference it can make. So we look at the logs again. So, yep, in our controller, we're still on Tomcat's thread. And then as soon as we jump into the scary dependency, it's actually on a different thread. And you can configure Hystrix to throw an exception if that doesn't respond. So the Hystrix thread is lost. It's gone into the oblivion of whatever client, HTTP client you've done. But you can still respond to your user on your application thread. Okay? Everyone get that? And actually, I maybe should have done raw Hystrix first, because it makes more sense when you see raw Hystrix, but we've got an example coming up. You don't need to do this for everything. So more and more, people are realizing that it's better to offer an async interface and let people make it synchronous. Okay? Lots of libraries do this now, because a lot of HTTP clients, all these libraries, they don't actually use your thread to make the call. Okay? They actually do it on their own thread pool and then just block your thread. But quite a lot of libraries now are giving you the future back, so you can actually block on that and time out separately on that. Things like the DataStax Java driver returns you a result set feature, which is a Guava listenable feature, which is a Java feature. So you can actually do your timeout separately on that. The disadvantage is that you get a lot of extra benefits with Hystrix that we're going to talk about later. So we didn't wrap our calls to the database in Hystrix, but we did use asynchronous way of communicating with Cassandra and timed out if something went wrong. So surely that's as long as any one person can talk about timeouts. So I'm going to stop there. Couple of take-homes, okay? So whatever you do, don't use network timeouts your SLAs. Okay? It's not going to end happily. Okay? Things happen even if there aren't problems in the network. That's not the only thing I'm talking about. So think of the resource acquisition. That actually is taking longer because it's waiting for a resource. We're going nowhere near the network right now. So don't just think, oh, I've got the super reliable network, I don't need to worry about this stuff. Okay? So what's next? So this one just seems like common sense to me, but not many people do it. I didn't do it. And that's basically don't bother wasting CPU cycles, etc., if you can't succeed. Who has been to the UK? Who's been to a post office in the UK? So there's some advice if you ever visit the UK. The post offices have the slowest queues in the world. It's a record. Okay? And if you're on your lunch break and you walk into a UK post office and you see this, you do not wait. You use your lunch break to go and sit in the park or buy a nice sandwich, okay? Yet we write a lot of software which sees this queue, this work that's backed up, wait around, and then time out in 5 seconds, even though it was never, ever going to succeed. And my kind of goal here is to convince you not to do this. And when you're using libraries like Hystrix, it's really easy not to do this. So I don't know where this quote's from. It certainly is not original, so I put it in quotes. And it's basically saying, when your application gets complex, you eventually send an email. Okay, everyone agree? Or you have a log system which sends emails, something like that. Okay, this is my version. As soon as any application gets complex, you have lots of queues or buffers and thread pools. You might not see them. They might be hidden inside your Tomcat or your Jetty or your libraries that you're using, but they're there. Do a thread dump. There'll be hundreds of them. Okay, and most of them are using Java executors, right? This is basically a really good thing that was in Java 1.5, I think, which basically is most of them are just a queue and a thread pool. You put some work on the queue, you get a feature back, yeah, and then the thread pool just works away and eats up the queue. These are so configurable. There are so many parameters for these, but we don't often do it, do we? We normally get something from the executors factory because that's nice and Java gives us that. How many executors from the executors factory, that's a tongue twister, do you think have a bounded queue? So would actually stop receiving work and not just essentially be a growing thing of memory until the JVM falls over? I haven't found one yet. There probably are some, but they're ones that I've most traditionally used. So, the fixed thread pool, single threads, the cached thread pool, all by default have an unbounded queue. So it means that a lot of the time when you're using libraries, etc., They're just using the defaults, and thus they have an unbounded queue. What happens to systems with unbounded queues, they exert no back pressure. They never reject requests. They eventually just get slower and slower and slower as more memory is filled up by things on queues, then fall over in a heap. Okay? That's not failing gracefully. Okay? And these types of queues are in drivers and HTTP clients a lot, which means you're going to come across this a lot more if you decide to go down the whole microservice woohoo, architecture. All right? Because you're going to have so many more of them. So this is kind of a warning to always know the drivers and things you're using. Always have bounded queues. Maybe you don't want a bounded queue. Maybe you've got 4 terabytes of memory and it's a batch job. Okay, that might be a time when you wouldn't want a bounded queue. But for any kind of like responsive reactive system, you want to bound your queues. And I was once integrating with a system. So these services were calling out to another system. And they had a requirement that they were integrating with us. They were actually calling out to one of our audit services. Now, they didn't want to break the user journey, so actually like stop someone from doing what they wanted them to do, if we failed or they couldn't send it to us. So they made it asynchronous. Not on the user thread, it jumped off onto a queue followed by a thread pool, okay, which sent it to us and logged an error if it didn't get a response, okay? They picked some big numbers for that. They thought, we're going to have 100,000, in the queue, 100,000 bounded queues. They got that part right. But then they decided that, obviously, if the queue's full, you want to fail and not ruin the user journey. And they said, yeah, we'll catch that in load testing to make sure we've done that. I was like, really? Just like the timeouts, we can test all of these drivers and queues really quite easily. Okay? So when we're developing our user service and it calls out to a pin service using a HTTP client, most of the time, the drivers are making this kind of thing configurable. Or if you're doing it yourself, obviously, you can make it configurable. What we essentially want to do is set, say, the queue size to 1, thread pool size to 1, set Wiremock to delay the responses so it doesn't get it back. Okay, so those two, so when we send in 2 requests, they're going to be going for 10 minutes. And then we send in the 3rd request. And that's a really simple way to actually understand exactly how your application will behave when it hits that peak load. Don't try and do it in load testing and fill up your real queue of 50,000. Make it configurable and be able to test it that way. Don't worry, they all get shorter, so I will finish on time. So who here's developed a HTTP API with JSON? Yep, we love JSON, we love HTTP. How many people have been integrating with a HTTP JSON API and got stack trace in HTML? We always get this, right? And it's because a lot of containers, they default uncaught exception, blah, 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 blah. But we don't do this. That's fine. I'm talking about who we integrate with. We don't make mistakes. But the whole point of this section is to realize that everyone makes mistakes. And everything you integrate with will do something which the design team or the architects or the developers said will never, ever happen. Okay? So here's the kind of things I really like to test. It's not that you're just not trusting them. You're also not trusting your driver, your client, okay, your library. So you get some really funky exceptions out of HTTP clients when you send it invalid HTTP. Or you just cut them off in the middle, okay? Or you send them really large messages. You actually work out how fault-tolerant your dependencies are, okay? So here's some of the things which I'll always have tests for. And the great thing about this, if you decide to go down the testing route of, say, mocking your driver to throw whatever exception it did on the 12th of December, 1942, then that's only correct then, okay? Every time you upgrade, say, a point release, they might change what they do. Because even though we mainly work in Java on the JVM, and we love types and we love compilers, we love runtime exceptions, okay? The whole way to just completely circumvent the compiler and the type system. And we like that because typed exceptions suck and we don't like monads. But what happens when they just change that? They go from throwing an exception to returning null. They can do that. There's nothing stop your code will still compile. What happens when we moved all of our services from Jersey HTTP client to Apache HTTP client because of a bug in Jersey? And we had tests like this which instantly found out exactly how that driver behaved. If we'd done the kind of mocking ones, we'd have just had to throw them away and start again. And this is where I'm going to be a Wiremock evangelist. Okay, I always joke that I sometimes talk more about Wiremock than Cassandra. So Wiremock runs in process for unit tests, and it can run as a separate process for these types of acceptance tests. You essentially say, given this URL, do this. And you can do happy path testing with this. What we're interested today is the non-happy path testing. So Wiremock has these awesome faults. So this is the JSON API when it's a separate process. This is the Java API. So you can get Wiremock to like do random data and then close. And it's hilarious what certain clients will do when this happens, okay? And how often it will change between versions. Or empty responses. So that's where Wiremock can help you. The other thing I like to do is to expect response sizes considerably different to what they say, okay? Fair enough if they say it's 10 bytes. If they send you 10 megabytes, you can fail. You can tell them to go away. But you do not want your application not to fail gracefully. If let's say, oh, they're 10 bytes, I'm just going to read it into memory. You're doing a few thousand TPS, and suddenly they send you 12 megabyte messages, okay? So all I'm saying is expect it, handle it, something as simple as, say, checking the content length, okay? Don't just expect that what the responses they say they're going to give you, they're actually going to give you. And that's why I built the similar thing for Cassandra. So I'm integrating with Cassandra a lot now, so I want the equivalent test double. Because Cassandra, you typically deploy over many nodes. You deploy it across multiple data centers. There are many failure modes which only happen when you deploy it across multiple data centers. Okay? So you can't actually create them in, say, your acceptance test environment with one node. So what Stubbed Cassandra does is Stubbed Cassandra at the protocol level. It pretends to be Cassandra, but you can tell it to do all of the failures. So Wiremock for HTTP, Stubbed Cassandra for Cassandra. Whichever technology you're using, you might need to make it yourself. Someone else might have made it. So next, knowing it's your fault. The biggest complexity, I think, of working in microservice environment is working out what on earth is going on. No longer do you have that one server with that big monolith and that one log. You suddenly have requests. One user request might go across 15 servers. Might go across 2 data centers. Who knows? Okay? So you have to put a lot more effort into developers as working out what's going on. And invariably, a lot of companies have a blame-orientated culture. They want to know what's going on. And they instinctively just blame someone else. So when we're developing all of these small services, you need to know how your dependencies are behaving. Okay? Don't trust their response times, etc. Measure them from your side. It's amazing how many outages where every single like node in every single service inside your system is showing a green light, but none of them can talk to each other. Okay? So like safety checking and health checks need to go, you need to have ones that go directly to your application, and you need to have ones that what I classify as like a spider. So you hit one and then it calls the health checks of the other ones and calls the health checks of the other ones. I can give you a report of like, I can see everyone, or I can see no one. What kind of things are you going to record? So timings are important, error rates, all these type of things, being able to identify bad services and bad nodes. Logging and tracing requests through your system is absolutely imperative. Okay? Suddenly, if Bill calls up the call center and says it didn't work, you want to be able to see their entire quest through all of your systems. You can't go to a single node and look at the logs and grep them anymore. Okay? It might be across 50 servers. So if you're rich, you typically buy what's it called, Splunk. We weren't rich, so we used the open source stack of Logstash, and Kibana. And if you're really advanced, you can use something called Zipkin. Anyone use Zipkin? We were evaluating it, but didn't use it yet because we had a elk stack for logging, and we could have an identifier go, basically between every single service. There was a HTTP header, which had a request identifier, which was logged. Zipkin takes a slightly different approach. You augment each of your services to actually push data out to a central service, and so you can look, and it will like show you what transactions look like. It's actually backed by Cassandra as well, which is why I like mentioning it, because I'm evangelizing Cassandra. And because what you generally find is that you take one of these off-the-shelf monitoring solutions, then you realize that it's actually the most high-throughput system, because everyone's sending. So typically, logging systems and metric systems go down when you're under load, which is exactly when you need them. So for Zipkin, the data goes to Cassandra. Anyone use Graphite? So Graphite is typically backed by, say, Postgres or an on-file format. You can actually run a version of Graphite which is also backed by Cassandra. Because typically, if you think every user request sends out 50 metrics to a server to record things, you can suddenly realize that, whoa, your biggest scalability concern is actually Graphite. And why would we use things like this? So there's a really cool library called, anyone use Dropwizard metrics, or it used to be called Codahale metrics? So that's for recording timings and counters and things, and you want to push them somewhere, because you can't go, oddly enough, you can't connect JConsole to 50 different nodes of your application. You need to push them to a central location. Graphite's great for that, okay? So here, the example which is on GitHub is using Hystrix, and it's recording these metrics, and we're going to show you some. So this is response time. It's actually average response time, which is a terrible metric. I'm just showing a point. What it actually is the device service is blue, so you can't see that one. It's all the way down here. Pin service is blue, all the way down here, under 10 milliseconds, okay? App response time, remember that the user service called them all, okay? And for some reason, it had to call them serially. That was doing okay, and then it shot up. Let's say we had an SLA of 200 milliseconds. We're still doing fine. You know, we're still well under 50. What you can see here is the user service started going up. So before you actually cease to meet your SLA, if you're constantly looking at dashboards at response times, you can like predict it and fix it. Go and talk to the user service guys and say, you know, sort it out. And at that point, you realize it's really important for each of these not to affect each other. So if you've only got, say, if one of your services is going really slowly, okay, let's say it's not even a mandatory dependency. If you're using the same resource pools for them, then that being down can actually affect the rest of your system. So one kind of lesson learned, I would say, is always use separate like connection pools for each of your dependencies. And Hystrix, this is an augmented Apache HTTP client with Dropwizard metrics pushing out the things. So I didn't write any code to do this, okay? I just used the instrumented version of Apache HTTP and basically set this. So in Dropwizard also has support for Codahale metrics, and we'll push them out. Hystrix has support for Codahale metrics. So Hystrix, you know, as it's counting failures and things, it will actually push those out if you just add this tiny line of code. And if you want to see the context of this, this is like in the equivalent of the Spring Boot, you know, application main kind of thing. A couple of lines of code, a bit of config to say where your Graphite server is. And I've got a Vagrant VM with Graphite as well. It's quite an interesting thing to install. So if you just want to spin it up and play with this locally, then you can use Vagrant off my GitHub for that too. Two more, and they're going to have to be quite quick. Okay? So they're very related. One is don't whack a dead horse, and the other is turn off broken stuff. Okay? So why would you whack a dead horse? I don't know. So we're going to go back to the architecture, and we're going to assume that one of our services is faulty. Okay? One of them is going down. All right? So the pin service isn't responding. So what do we do? Do we time out? Okay, we've got that sorted. But what we can actually do is fail much quicker. Because if we record metrics about the response time, etc., of our dependencies, we know when there's no hope in it ever succeeding. I'm not suggesting you write this stuff yourself, by the way. The answer is Hystrix. But what we can actually do, though, is do the thing called circuit breaking. Has anyone heard of the concept of circuit breaking in software? I probably won't take too much time on it. I first read about it in this book quite a few years ago. But essentially, you wrap these dependencies in what's called a circuit breaker. If it fails too often, if it's all failing, rather than continuing at whacking a dead horse, so the pin service team are frantically trying to bring up some new instances, then you flood them with requests and take them down again. You know, you say, our team's better than yours. What you can actually do is give them a break. So rather than continue to hit the dead horse, you can decide, nope, I'm just going to fail the request. Which isn't that great, okay? But we're going to see how we can fix it. So this is an example of raw Hystrix. So we've got 3 dependencies. This is a Hystrix class, which we've extended. And we go to all 3 of them, we call execute. Right? There is a future-based API as well, and also an RxJava one to get you an observable. And all we do is return them all connected together. Simple, okay? That's not the real service. Sky do more than that. What does a dependency look like in Hystrix? Okay, so you extend this class, you tell it the return type. What does it do? This is a Apache HTTP client. It calls out, it executes it. If the response status isn't 200, then it blows up. If it isn't 200, it assumes that the response is going to be true or false by doing a Boolean value of. What could go wrong here? Nothing, I assume. And the great thing about this is, because this is a Hystrix command, Hystrix is constantly keeping statistics about how successful these have been, and will circuit break for you. Don't worry, if you don't want the circuit breaker functionality of Hystrix, you can just turn it off. But at some point, someone's going to say, actually, we'd rather some kids watch Game of Thrones than us have downtime. Okay? Because it's a choice, right? It's a business choice. That's not a technical choice. They should decide to you whether you want to be... It's almost like cap theorem all again, because it's like, do you want to be consistent in your behavior, or do you want to be available? And sometimes you pick available. So with Hystrix, you can actually do this as well. You can override an additional method, which will be called when it's circuit broken. So that basically means that if the pin service goes down, you always just let people pass. You say, yep, their pin was fine. This is kind of hard to convince businesses to do, I've generally found. If you say, I want to turn off some of your awesome checks and functionality, okay? They just think, no, parents will be uproar, they'll complain, okay? So you're not going to convince people to use circuit breakers right away, okay? What you might be able to do is convince them to turn off broken stuff. So what generally happens is, you know, the pin service goes down at the weekend, you get called, okay? It's a Manchester United game, or it's Game of Thrones premiere, okay? Everyone is really upset. They're like, this is our biggest, this is where we make most of our money. So what you do is you say, would you like me to just turn off pin checking for a bit? And you think, turning it off is really quite simple. You don't need business permission from that. It's an if statement. And being able to like set some dynamic config, say with JConsole or with Zookeeper or whatever you use for config. Okay, and the manager says, yes, you're the hero. Okay, so you turn pin checking off and you just default to true. Next week, they call you again and say, do you mind clicking that button that I didn't know existed again? You say, yeah, I'll do that. The third time it happens, they'll generally get sick of paying your weekend rate, and then they'll say, could you automate that for us? And then you say, I certainly can. And that's when you get like the business buy-in, I think, into doing things like circuit breakers. So that brings us to end. So hopefully you got something out of that. If you want to play around with some of these texts and you can't be bothered building it yourself, all of the example codes are all in runnable either Dropwizard or Spring Boot applications. Some links there to Wiremock, you know, being a Wiremock evangelist that I am, and Saboteur. And if you're interested in Cassandra, there is actually a completely free conference coming up. So I'll post this link on Twitter. So if you want to come along and hear a whole day of either use cases or like there's a beginner track and a more like advanced use case track, then it's free of charge. So I don't think I've got any time. I've got 1 minute for questions. Any questions? Nope? Brilliant. Thanks for listening, guys.